So, people, please sit down. We're gonna reconvene. We're going to start again. Hope you're all refreshed after the break. Because the next speaker is gonna wake up the crowd. He's Greg from FUNMIN, and the floor is his.
Thank you. Hi, everyone. So first of all, thank you very much to those who have funded us and allowed this project to happen. I'm not sure if I will live up to the expectations of livening up the crowd. So sorry to be an imposter on the current day's schedule, but I'm Greg. I'm attached at the fist with my partner Devis. Because of this pandemic, we've had to detach ourselves from being at the hip. This is the FUNMIN project, which spreads across Granada, Oviedo, Grenoble, Utrecht, London, and then our only industry partner, Cambridge Carbon Capture. However, during the project, and despite this pandemic, we've been able to grow partners in Rome, and also two Canadian partners as well that have come on the project, and one Roman industrial partner. Where's the slide changer? Right in front of me. Yeah. Okay, that's forward, isn't it? Okay, I put this in because the relevance to CCUS, I'm going to try my best to understand where we sit in this. So I found many examples of this, is how much is going up, how much is going down. Where's the carbon stored in what forms? There's many variations of this. I'm not sure all the numbers are correct, but they give us an idea. What I've gone and done is try to redo this so I can understand it. It's a little bit simpler to understand. I think that the problem mainly, and is there a go back? The go back slide is how much goes up.
This one, and then you can use the microphone.
Can you hear me?
Yes, but not when you're...
Not when my head turns. Okay, all right. I get used to the style of delivery. I need the headset. Anyway, okay, you're right. So how much goes up and how much comes down? The important thing is that there are these key points where we're breaking the balance in that. So what I've tried to do is try to look where the majority is going up and why not a sufficient amount is coming down. And I think this is also one of the problems. A lot of people that are doing the capture and storage sequestering are trying to help solve the problem to reduce what's going up. But what FUNMIN is trying to do is try to increase how much we're putting down into solid, fixed, or in solution carbon, and keep it there, including methane and other sources. All right? So the numbers, the fluxes there in red, represent what we're doing. That's the FUNMIN project. So what it involves basically is capture of the CO2. We have a dissolution and formation of CO3₂-, which is an ion, which is a driving force, chemical driving force, to making magnesium carbonates. And the amount is in megatons. It's not quite the gigatons that we need, but at least it's somewhere along the way of usage. Now, we've heard the joke about Coca-Cola. We can only use so much Coca-Cola. Where are we going to put this carbon, CO2? So, and the uses of this, the reuse, they need to be profitable. Because let's be real, if it's not profitable, it's not going to move quickly enough. So this picture here, where you see the block of CO3, this is magnesium carbonate, a form of it. We can use magnesium carbonates, and there are different forms of them for many different parts of industry. And that's the goal, is to generate more solid blocks, control the mechanical properties, understand the chemistry of it, both at the micro-nano scale and the macro scale. So there's also these quotes about unraveling the fundamental mechanisms. That's what we're trying to do in FUNMIN. So there's the project. Originally, it was supposed to end in March this year. We've had an extension, thankfully, and that's been good for us. It's given us some time. We're the smallest. We're the baby of the ACT family. We didn't have huge funding, but we had enough that we were able to get things going and use the extra time to do something. So initially, what we wanted to do is to make new generations of these carbonates with industrially relevant solutions, while also understanding the nanoscale properties and the nanoscale mechanisms and dynamics that were ongoing. And the idea was to make next generations of carbonates. Next generation after next generation should be improved in terms of how quickly we can make them and the properties that they have. And we've been able to achieve that to a degree, as you'll see. Here's the key achievements. I'm not going to read them out to you. The key achievements include tackling those key steps that are the rate-determining steps for industry, where you got to put pressure and temperature to speed them up. We don't want to put pressure and temperature. It costs us energy or money. We want to quicken the process. We also want to control the properties. So what we've started doing is we've been doing computational simulations, neutron scattering, which maybe you know about synchrotron radiation. Neutrons are even at a larger level. We can use realistic blocks and samples that are representative of these materials. And that's what we've been able to do, is to engineer reactors and some of these flow cells for real-time tracking of these carbonation processes. So one of the key things is that, and you'll see, and I'll not turn my head and as best I can, what usually you do in industry is you raise the temperature. And what this is that magnesium likes to hold on to things in 6 ways. Just like a race car, you have a 6-point harness, it holds you in place, better than your 3-point harness, seatbelt. Well, the same thing here, the ions are held in place. That's why magnesium, it loves water, okay? So what the key is to get the water off magnesium. What you do is use temperature to do that. And so you want to take some of the water off first to make magnesium available to react. We got a cover article on this. We've had, I think it's 9 publications so far from this. The most important thing is we've grown, have more partners now. So as you see here, we're trying to show a clever figure here where that's the black hole that it goes into. We're trying to achieve that black hole where we get them off and now allow this reaction to proceed. Okay? And so what we've done is computationally, we've made a database. Why? Because in nature, you have impurities that come from microorganisms, bugs, bacteria, sulfur-loving bacteria. They release these impurities that catalyze that aggregation and transformation. Similar to when you poach an egg. A small spoon of vinegar aggregates the egg. It's the same thing here. So which ones are the best? Which ones are innocuous, non-hazardous, not costly? So we've made a database of that industry can use, or we can use. We also look at the molecular dynamics, what's going on at the nanoscale, how these things, how the egg aggregates with or without vinegar. We want to keep it together and then grow those particles into something we can use. This all sounds very theoretical, doesn't it? Where's the real world? Come on, Greg. Give us something we can chew on. Okay, all right. So we start doing experiments in Grenoble where we're starting to heat this up. We mimic what's done industrially. We don't disregard it with high temperature, high pressure. Let's see what's going on when we do that. And we show the formation of hydroxymagnesite, then to magnesite. Similar to the Dolomite Mountains, calcium magnesium carbonates. Marble is a calcium magnesium carbonate. I forgot to mention before, how much carbonates can we make? Mount Everest is about 160 gigatons, it's estimated. We need a few Mount Everests. We need a few Mount Everests. That's what we need to do. That gives us an idea and scale of how much of this that we need. So again, I said this sounds all very theoretical. I'm a theoretician. I do a lot of experiments, neutron scattering. Give us something real that we can touch. So we started building reactors, literally in the backyard. The Homer Simpson model was before this. This is the second generation, this one. We built reactors to do this and track it. We do it at the nanoscale and we do it at the macro scale. Now what you see here is 2 different forms of the carbonates. We can control if they're crystalline or amorphous, disordered. Why do you want a disordered system? Because they change. And as they change, they release the magnesium. They can exchange for cadmium, for example. They remain carbonates. We can use that driving force of physical change, chemical change, in cementation. Don't believe you, Greg. So we built a reactor that can go on a neutron beamline. Now, neutrons, believe it or not, at a particle accelerator are non-destructive. You've got this beam, about 7 centimeters in diameter with high-energy neutrons, but they're not destructive. They can scatter off of matter. When you scatter elastically, that's called diffraction. We've heard of diffraction. When you scatter inelastically, you might be familiar with infrared or these other techniques. We get an idea of the dynamics, the motions in there, the energy involved in these processes. So we inject CO2, we carry out the reaction in real time, the industrial reaction using the dirty stuff, impure. I don't want model systems. I'll go to the model systems later. What we also made sure of is that the reactors can be reused. Watching the carbonation process and its interaction with the metals. We want to know if we can build these reactors and flow reactors to do this. Great. You can make a few grams. Good for you. We need gigatons. So what does this tell us about? Quasi-elastic scattering. It sounds like a non-committal relationship or something. Is it elastic? So it's quasi-elastic because it's very low energy. You track translations, rotations, and vibrations in the whole material while the reaction is ongoing. This elasticity, if something's more tough, if you form aggregates, it's going to be more elastic. So we track that in real time. We watch our solutions, we watch our reactions in real time. Don't believe you, Greg. It's too small. So, second generation, well, third actually. We don't show the first one because that's embarrassing. You got to see it. I actually should have shown it. This was just built. We're doing this grassroots. We're doing this stuff. We're designing this. These are modeled after ship propellers for giving the turbidity that you find in tidal pools, in flows of water, how carbonates are formed, how mountains are formed. We want to mimic that turbidity. Does it work? Turn it on. Go. We're building in for high pressure. We're testing for pressure. Put the water, put some brine. We can also do industrial brines, the output of desalination plants. You get the flow, physical flow, the heat, and you have a very high concentration of ions. Bam, precipitation right away. Look at those. So this is not just a chemical process. This is a physical process. It's a physical process where you start forming, gotta get the right button here, stalactites. We're forming the aggregations. When we put additives in, we get carbonates faster, room temperature, room pressure, right? That's what we want to do. The other thing is, we could start to control the particle graininess and sizing. Why is that important? What are you going to do with all this stuff? Okay, you got a couple Mount Everests in your backyard. What do you do with it? Well, this young lady here, who happens to live in Rome, I know her pretty well, says, stop all this playing around in neutron and particle accelerator facilities. Let's do the real. So we did the real. We made 2 tons of concrete, adding our own carbonates and doing tests. Proper facility for testing, all the porosity that was just mentioned in the last talk. We're looking at the porosity, fracture toughness, tensile strength. You compress them. We do that after 1 day, 3 days. We do the ISO standards as well. You fracture them. We're trying to reproduce the fracture toughness with a percentage of carbonates in them and agricultural wastes in there. So I'll leave this up for a second in my last 3 3/4 minutes. Grainy or sloppy. Why is that important? So that same young lady happens to know a lot of the Romans. You can put these into silos once you dry them. And they can sit there. They're stable and they don't do anything. That's important because the silo, as it comes out the silo, if we succeed in making these carbonates, now we're going to hundreds and 1,000 kilo. If you succeed in making these, what are you going to do with them? You put them in silos and they can sit there and store. Or can we put it direct into the truck? So we're working with these guys. This is a pile of aggregate from recycled concrete. You cannot recycle concrete that has plastic fibers in it. So they recycle this. You use energy to grind it up. There's the pile of recycled concrete, the ceramic bricks, everything out of Rome. We're putting our stuff in there, making it sure it can be stored outside as well, go through the silos and everything. And we're also testing, if you know concrete, cement slump. It's important. When you pour these pillars, you pour in the cement, it has to go down to the bottom. You want it to fully self-compact. And you also use vibrations for that. So we're doing all these tests at that level. That's what we're trying to do. So we're keeping it sustainable. That's the new term. We're making sure that there's a whole waste stream for all of this because we're growing into 2,000 kilos when we go to do these things. We've put in agricultural wastes, which we have access to, that nobody wants. It's like fly ash many years ago. Nobody wanted it. They paid to take this stuff. Here, take this off my hands, bury it in the backyard, right? So that was what they're doing with this waste here. Well, now there's a problem because just on the 26th of May, not too long ago, they want to stop the demolition of buildings. It makes sense. And that means that that pile there might be going the way of fly ash. They've been reliant on the aggregates, and here we come along with our own aggregates to help replace that. Putting them through the silos, we're putting them into concrete, so we're able to do this process from the molecular level, nanoscopic, that's what you need these glasses in the computer for, to understand all that stuff, and we're getting out there with that young lady there and helping shovel this stuff to do the tonnage and testing it to satisfy ISO standards. Maybe we can put a bit of carbonate, maybe we can put some of those carbonates into the concrete, retain the properties, maybe elevate some of them. The resistivity and the fracture toughness is what we're testing right now. With that, thank you for your ear, and thank you for the funding from ACT and those else who have funded us, and thank you to the new partners that have come on. I'm really surprised because normally it's very hard to find them. They've spontaneously come and found us, and we're really doing a good job, I think, of growing the project. And thank you for your ears. Am I to time? I gotta practice the head thing, right?
Yeah. Time for a quick question. Anybody?
Department of Energy's coming for me. Uh-oh. Put my hand.
Can you give a couple more specs on, I guess, grain size in particular?
For which? Grain size.
Grain size, the largest you could get.
So the largest? Mm-hmm. Well, as you saw there, so these are a few millimeters. We can probably grow them more. Additives change that, as I was showing before. You get the slurries and how you dry them as well. What additives are in there, especially the salts, concentrates and salts, the type of water you're using, temperatures and all that. That's what that sort of propeller-shaped thing, which makes the turbidity, makes vortexes. If you notice, the reactor was hexagonal. You make small eddies in the corner. So we're playing with all that. Maybe we can grow them larger if there's a need for that. So, I mean, what's the goal? Centimeter?
I was actually going to follow up and ask you, obviously, concrete, 70% to 80% is actually synthetic aggregate, various sizes. I guess what target range are you looking for? Because it seems like with the millimeter scale, you're hitting more of an additive, which is a smaller volume of that 70.
Of course, and you can break those up ultrasonically or whatever, and we can control that. So you could probably control from probably 100 microns up through to possibly a centimeter, and that would be a follow-up project. That's a good question, because do we want to make synthetic gravel, for example, or aggregates that are at the 5 centimeters? So there's the classifications for each of the additives, right? They're called fine particulate and otherwise. So.
Okay, cool. That helps that. Thank you. Sorry, Amishi, I forgot to give my name.
Thank you very much. The next speaker now will be from the NEXTCCUS project. It's Mr. Mahmoud Zedenel from Italy. It's an Act 3 project, and we're happy to hear about it.
Thanks a lot. Hello, everyone. Thanks for all the organization for the very great in-person conference with different topics and different branch of science. Today, I am going to speak about our projects, and which may be a bit different from the other concepts, but I will discuss how it can be related to all the parts of the carbon capture and utilization, and also the storage part. Okay. I am Mahmoud Zendedel from Italy. We are coordinating this project. It's a company. We are working with different concepts, especially now for the research, and from Rome. Okay. Maybe we can escape very fast from this slide. Everyone knows what is the situation and what shall be done by all the countries and by the policies mainly in all the world. So here is this emission systems in all the world, how this percentage of the emissions comes from different branches and different sectors. As you can see, most parts comes from the energy production from this emission, and some other parts which is related to different needed of the human. And now I can briefly tell what is our concept in this project in NEXTCCUS system. It's something to, how can I say, storage the renewable energy. We can say something to store renewable energy for the lifetime, and how we can do by using the circulation of the carbon, which is CO2 in this case. The system, maybe you know the electrocatalytic systems. It's very famous for hydrogen production, water splitting, and production hydrogen, and some traditional ways for the conversion and reduction of the CO2 is by reaction of the hydrogen with the CO2 molecule to produce, for example, one of the main things. This is a liquid methanol. I will tell you why it's very important. And in this case, we can circulate this CO2 emission by conversion to this liquid structure. There are different types of the energy sectors for the recent years. If we can divide in the 3 types for the energy sectors in the hydrogen-based strategies, and for the batteries for storing the electricity from renewable energies. And there is another types, which is liquid systems and liquid molecules, which can be stored. And you can see here the difference, how we can difference in the policy making, how big are the plants, the difference, how heavy are the systems for production a specific amount of energy, and how amount of the investment is needed, the difference between these three types. So and this is one of the things that we can say why we select this methanol as our product and this strategy. So now going to methanol. Methanol is very famous chemicals. Most of the plastics and other materials which we are using is coming from methanol, from this conversion. Is one of the base material after conversion of the natural gas, and most of the methanol at the moment is producing by the conversion of natural gas. And other chemicals, more formaldehyde is very famous for all the plastics, and some other olefins, and some parts for the mixing with gas oil and in the energy sector, it comes from the methanol, with 98 million tons of the demand per year. Now I'm going to more specific focus on the e-methanol. This e-methanol comes from when we use the electricity and use the carbon, we use the CO2 to convert, to reduce this CO2 to methanol. We can say this classification as the e-methanol, but we can classify in three different ways of this conversion of the CO2 to methanol to produce this e-methanol. First one, which is more traditional, and there are some plants around the world which are using in this way. They have these electrolyzers. These electrolyzers split water, produce oxygen and hydrogen, and this hydrogen in another reactor under the catalytic and under pressure convert to methanol as a product by reaction with the CO2. There are another possibility of this system to produce syngas, which is coming from the hydrogen and CO, and convert this syngas with reaction with CO2 in another reactor to produce methanol. The interesting things that are still not developed, it's very low TRL in this during the years, and it's very interesting. The things that doing usually the trees, the nature is doing this method, which is direct conversion of the CO2, don't using any water splitting or producing any hydrogen, and then convert some very complex system. This is for the direct, for reaction of the hydrogen and CO2 under the electrochemical way. Why, now, in the parentheses, I say why we need electricity, because you better know that this dissociation of this bonding of the CO2 need, as a thermodynamic, need energy. So in any case, we need this energy, but we can manage the catalytic way, and we can manage the kinetic of this system. Okay. As some case studies, some case plants which start to industrially produce e-methanol recently. Very famous is George Ola in Iceland, which is producing 4,000 per ton methanol from conversion of the CO2. All these plants use the first strategy, which I told, by passing the water splitting. E-methanol is very famous now as a methanol hub with Siemens and some other companies are still start to put more investment for these, mainly for application in the fuel sectors. It's very good clean fuel to first alternative for the replacement in the fossil fuels, especially for the marine transport. There are some big ships at the moment are changing to the methanol as a fuel. So now, coming to the next CCUS, This project is based on the 8, and I can say 9 partners from different countries. We are 2 Italian. Italy is our coordinator. We are in Italy as a coordinator and some part of the project. And we are CNR from Italy. And 1 partner from Hellenic Mediterranean University from Greece. From England, we have UCL. From USA, we have 2 partners which join together as 1 partner, which is Argon Lab, is the main partner of this project, but Indiana University is very famous for producing some specific materials and vaccines, also is joining to Argon as a subcontract. We have an famous industrial partner from Romania, Griro, and we have 2 partners from France, University of Lyon and University of Paris. So, as I told you, our overarching aim is to conversion to the CO2. It's the system that we are going to realize is made all this capture and conversion and storage as one system, not separate and complex. This is a type of the reactor which can absorb the CO2 on the surface and immediately by the electrochemical reaction and the new materials that we are going to develop. And we already developing some technology parts in our company. It can convert very fast to methanol and selective to methanol. This methanol going to water and separate from water and can be stored for long term as a sector of energy which can be used for production of energy or as a fuel. Different objectives of the project, as you can see, we are going to develop this efficiency of this system and scale up all this lab scale strategies to larger scales and realization prototype reactor for doing this concept. We are going to specifically put some tasks for the for the impact sectors and the economic concepts of the CO2 and methanol both. As you can see, at the moment we can claim we are close to TRL3 based on the project that we already run and the reactors that we already have for this kind of direct CO2 reduction. By this project, we are going to develop this system by the a specific device structure and using some new materials which is developed in the USA. And using this kind of materials in all parts of the electrodes and membranes, which I saw should be very interesting for collaboration with other projects as I saw in today. And this system can be a scale up. A specific challenge I can going faster. There are a lot of challenges which should be covered and should be addressed during this project from the scientific, technical, and commercial challenge. And the project that we are going to use is using the gas diffusion electrodes as a specific systems for increase the absorption of the CO2 and reduction very selective, and using the specific patent that we have for the piezoelectrocatalyst and two-dimensional transition metal maxings, which I told developed in the USA. We have 7 work packages, mainly beside the work package 6 and 7, which is real communication and coordination. In the first work package, which is starting running, and there are a lot of results until now for the lab scale development of the system. And then we have also at the same time for the simulation, modeling, and phenomenology of this system. And then next year we will have this scale up when these results coming from this 2 work package to a scale up, and at the final point for the industrial validation of the system. At the supporting of this work package, we have sustainability assessment. I can pass from this. We have also some advisory boards from different companies that we are going to 2 big companies are the steel producers and the energy producers which we are going to test as a final point of this reactor, which we already have this another project, a national project with them. And thanks a lot. Thanks again for organization and all the project partners to give me this time. We are ready for any collaboration for other projects and for any detailed discussion of the system. Our website is going to launch in a few days. It will be online. It's designed, but it takes time to going online, and you can refer to this website. I think after, it's not working now. At the top. In any domain, EU, COM, it's not different. Okay, thank you.
Thank you very much. Mahmoud, he's here. If you see him in the next break, you can ask him all the questions you have on the electrochemical conversion here. Thank you very much for your contribution. And the next thing I need to announce is that we have so thank you. Next thing I need to announce is that we have a problem in the program because it's 3:30 and we don't have a break now. We have Coca-Cola instead. So the Coca-Cola project will make its presentation because we are in the usage session. Then we will have CooCE online, and then we will have a break of 15 minutes and reconvene 4:15 for monitoring. But first, the floor is for Coca-Cola. It's an Act 3 project, so it started last autumn, and we have here John Blackburn instead of Victoria Adesanya, who will tell us all about it. Thank you, John. The floor is yours.
Thank you. Yeah, so let's dispel a couple of myths. I'm not from the Coca-Cola Corporation, and this project has absolutely nothing to do with Coca-Cola, I'm afraid. So I'm representing the Coca-Cola Consortium on behalf of Victoria and my other colleague, Damien. I'm a mechanical engineer by training, and this is an electrochemistry presentation, so I will try my best. To be honest, it probably would have been easier if the project was about Coca-Cola for me to present it, but we'll see how we get through. If anyone would like to ask any difficult questions, then my ambition is to take exactly 15 minutes, so you don't have time to ask them, and then hide at the break. Okay, I've been given a slide set to present. I've got a few corporate slides at the beginning. TWI are the coordinators of this project, and if you don't know us, we're a UK-based research and technology organisation. We also undertake training and examination worldwide, and our parent company is a professional engineering institute that awards chartered engineered status in the UK. From an R&D perspective, we are headquartered out of the UK. We're about 600 staff, and we have 13 global offices to deliver training. Our core knowledges are very much around understanding how structures work, how to fabricate them, how to make sure they are safe, and how to ensure their through-life integrity in the various disciplines that I've listed upon there. Now, my colleagues that are involved in this project kind of sit in the corrosion and corrosion prevention area. And I have a background in manufacturing and joining and mechanical engineering. So I've spent the last few days reading about this project and trying to understand it as best as I can. So to put it briefly, the intention of the Coca-Cola project is to develop and apply some state-of-the-art advances that the consortia have developed over the past few years and overcome the scale-up challenges and produce an integrated room temperature carbon capture and usage system to produce multi-carbon products such as ethylene. So by, I guess, laboratory-based, it's going to be a kind of small lab-based system. And what it will do effectively is allow us to take CO2 reduction and extend it from producing gases such as syngas or methane and move it towards multi-carbon products such as ethylene. The project began for the UK and the Grecian partners in Q4 2021, and then for the USA partner, which is Idaho National Laboratories, in Q1 this year. We've got a relatively modest budget of a little under 1.3 million euros and about 2 years to complete this project. So this is the project consortium. I've talked a lot about TWI already, but we're joined by UK partners, the University of Leicester, and their surface engineering activity there, as well as Technovative Solutions Limited to do life cycle analysis for the project. And then outside of the UK, we have Centre for Research and Technology, Hellas from Greece, and Idaho National Laboratories in the USA. We've also got NSG Group, which is the parent company for Pilkington. So Pilkington is a rather famous glass producer, and they are providing industrial steer to this project. So the project drivers, it's about carbon capture, but it's also about then using the carbon to make something that is economically viable. So we know that there are markets for electrically produced chemicals emerging. We've talked a little bit, or we heard about methanol previously. We know syngas is already established, as are other chemicals. And there are pilot plants. I think there are a few pictures in the previous presentation for some of the more simpler reactions that form single carbon compounds that are now live and producing relatively modest amounts of these chemicals. But there's also quite a strong economic case to make more complex carbon compounds. And in this case, we're looking at ethylene. So we have a little graph here that effectively shows the market price that you can charge for a particular volume of ethylene, and then the energy content that takes to make it, and then ultimately the business case for making it using electrochemical methods above certain megawatt hour rates. And you can see you've kind of got methanol there, you've got ethylene here, ethanol and propanol above there. So ultimately this project is focusing on ethylene. Worth noting that the current manufacturing methods for ethylene are very energy intensive and they produce quite low yields. So the intention is we'd create a kind of base for production of multi-carbon compounds after ethylene that could use this technology. So this is the kind of project concept. Effectively, what we do is we take some CO2 from an industrial user, so out of a flue gas. We use some kind of a solvent, an amine-based solvent, to capture the CO2, and effectively we're trying to look at something that is a kind of phase change approach here. So we're looking to then split the solvent once it's CO2 rich into a kind of rich amine, and then put it into an electrolyzer. This electrolyzer will make use of some novel technology, particularly around copper electrodes, that will allow us effectively to produce a variety of different gases, but in particular there'll be ethylene, there'll be carbon dioxide, and there'll be hydrogen. And then we'll use some novel separation technology to separate the ethylene out as well. And there's kind of a threefold benefit here. We can operate this concept flexibly, so we can take electricity at its cheapest, or perhaps when it's being overproduced by renewable energy sources. We can create value-add chemicals, and we can also reduce CO2 emissions by taking it out of existing production from the flue, and also replacing kind of incumbent CO2-heavy manufacturing concepts for ethylene. This is the project timeline. We've started the project back in November of last year, so we're about 6 months in now. So we're coming to the completion of work package 1, a little bit delayed because Idaho National Labs got their funding a little bit later than the European partners, but the ambition of the consortium is still to complete by month 24. So I don't have any results to share with you today. Perhaps what I'd like to do is just share with you a few more details around the project and some of the key innovations that we'll be focusing on. So the project consists of 9 work packages. Effectively, the ones where the innovations happen are in work packages 2, where we're looking at the kind of amine-based solvent to capture the CO2, and then We'll be looking at work package 3, the development of copper-based electrodes, and turning those into, copper-based catalysts, and then turning those into larger electrodes in work package 4. And then work package 5 will look at the kind of membrane system for separating the gases, and work package 6 will look at the electrolyzer design and this construction of this lab-based demonstrator. Work package 7 is a kind of overriding work package looking at the life cycle analysis, so carbon footprint and sustainability assessment. So a little bit about the carbon capture. So we're going to collect the carbon from a dilute source, i.e. a flue, and use a kind of switchable amine solvent system. Effectively, that allows us to create a kind of multi-phase output. So we put the CO2 in, we put the solvent in, and out of that we'll end up with 2 phases. We'll end up one with a kind of CO2-rich phase that we'll push into the electrolyzer, and then we'll end up with one which is a relatively CO2-lean phase, which we can put back into the solvent and then back into the absorber. So in Coca-Cola, some of this technology has already been developed. So in Coca-Cola, we're going to undertake a kind of detailed characterization of the vapor and liquid phase compositions, density and viscosity under different operating conditions, and hopefully to allow a prudent solvent recipe selection. We know from previous research from the consortium that copper metal surfaces can produce ethylene as kind of one of a mixed product for many years, but they do get very inconsistent results. So you have low efficiency, and often you get many other byproducts produced at the same time. There's been some good recent research that has basically talked about how if you structure the copper catalyst correctly and then the electrode correctly, you can get increased yields, and you can also move that towards higher efficiencies as well. So the challenge is the initial research is looking at cost of single crystal or nanostructured catalysts, and that's quite prohibitive for scaling this technology up. So in Coca-Cola, we're going to look at more industrially accepted technologies, such as thermal spraying and cold spraying techniques, as well as electrodeposition. So thermal and cold spraying are effectively methods of taking bulk forms of copper, usually in wire or powder, and putting them through a gas gun, maybe with a bit of temperature, and depositing them onto the surface into a new structure. So the idea is hopefully we can mimic what you do with a single crystal or nanostructured catalysts, but in bulk form and at low cost. And then ethylene separation. So this activity is going to be led by Idaho National Laboratories. They effectively will be looking at a multi-step separation process, as well as the adoption of a kind of hydrophobic polymer involving complex silver salts that I don't really understand. But if you want to ask someone, then please catch me at some point and I can redirect you to the right person. And then the electrolyzer development as well. So this technology has already been demonstrated for syngas. Critically, what we will do is add in the copper-based electrode that will allow us to deliver a liquid, as well as then use the electrolyzer to create ethylene instead. Okay, so this is just about my last slide. I see my plan is nearly complete. My time is nearly up. This highlights how the different project partners are going to work together. So we effectively have a Pilkington Group advising us about the carbon emissions and providing effectively steer on what the CO2 output will be. SURF will be looking at the amine-based solvent and the phase change approach there. And then TWI will work in partnership with the University of Leicester to develop the catalyst and then the electrode, and then passing that on to Idaho National Laboratories to incorporate in their electrolyzer, which will also involve the ethylene separation technology they're developing to ultimately produce small amounts of ethylene on a lab-based demonstration. So finally, I'd just like to acknowledge the other project partners, as well as my colleagues at TWI, the various funding bodies, so the Department of Bays in the UK, GSRI in Greece, and the US DOE, and then the organisers of today, and of course the ACT funding body. So thank you very much for your attention.
Thank you very much. We have 1 minute for a small question.
Be gentle.
Amishi, DOE, sorry. I may have missed it, but did you perhaps give an overpotential or voltage of the electrochemical cell?
Let's talk about that over the break, shall we?
Okay.
Yeah.
We will thank John once again, and we will move to the next speaker. Thank you very much, John. The next speaker is from CooCE, and it's Thomas Morosinotto, and he will be with us virtually. And you can see him over there. Thomas, welcome, and please tell us all about CooCE.
Okay, good afternoon, everybody. I'm really sorry I was not able to come in person today, so I'm still relying on this online presentation to present you our project that we just started a few months ago. And so we are going to use a different approach to what I heard today. So because we in our project, we would like to use the power of biology or living organisms and their ability to fix CO2 to make molecules and materials. So these are the partners of the project. Actually, the next slide is clearer. So we have partners from 4 countries, so from UK, Denmark, Italy, where is the University of Padova, where I'm working, and Greece. And in each country, we try to have academic partners together with companies so that we can have them working together and more closely one to another. So our idea is that we want to try to use, as I said, living organisms to recover CO2 from industrial emissions, so from biogas and exhausted gases, and convert this carbon into biofuels, in the clean biofuels and materials and chemicals. So as I said, this concept of the project is supposed to work with any CO2 gas streams, but we selected one specific stream to prove our approach. But at the end of the project, ideally, we should be able to apply this to other to flue gases and other CO2-rich streams. Sorry. Okay. So as I said, our working gas for the project will be in particular biogas, and for that we are collaborating with 2 companies, that are one in Italy and one in Denmark, that are basically biogas producers. And so biogas is actually a gas mixture when we have the methane, that is the energy carrier that we are interested, but we also produce a lot of CO2 from the digestion of the biomass in these big vessels here. So the idea is that we want to of course to clean this methane to have a better fuel, while at the same time using this CO2 to make useful material and chemicals. So this we will address this overall objective by using parallel approaches. So in one case, what we will do is that we will take this biogas and use excess renewable energy to produce hydrogen, and use this hydrogen to feed bacteria that are able to use the energy from hydrogen to produce methane. So the idea is that by taking biogas, we will do the so-called biogas upgrading by converting the CO2 included in the biogas into methane. This This approach has two objectives. One is that it is able to balance the peaks in the electricity grid due to the increase in the installment of renewable energy. At the same time, we will produce a better fuel, better methane, more rich in methane, and with less CO2. In parallel, what we want to do is that to using the same gas flue, biogas, we want to use this gas to make materials. And so we selected two different kind of materials that can be, as we are going to see later, converted into different bioplastics. So in the first approach that is going to be carried on particularly at DTU in Denmark, so they select at the lab scale some bacteria that are able to grow on waste, so organic material contained in waste. So this waste that mainly contains sugars, and using the energy from these sugars, they're able to convert the CO2 from the biogas into biosuccinic acid. So at the end, the two products will be, as before, a cleaner biomethane, but also this biosuccinic acid. So as I said, they already proved this idea at the lab scale, and during the project, they will build a pilot where they will scale up this production, and then also scaling up everything, all the phases, the downstream processes that are needed from the bacteria fermentation to extract all the final product of biosuccinic. The third parallel approach instead is the one that we'll pursue specifically in Padova, where we will again take this biogas, and the objective here is to produce clean biomethane, but together with another material that in this case is polyhydroxyalkanoate, that are monomers that can be converted into bioplastics again. So again, here we will use bacteria. The bacteria that we selected are two kinds. One bacteria that are called cyanobacteria that are able to do photosynthesis. So basically they use the energy of the sun to convert this CO2 into these monomers. And the other kind of bacteria instead are heterotrophic. So they use basically sugars, again coming from waste streams, to fix this CO2 again into these bioplastic materials. So we started with the lab scale results, and during the project we will again increase the scale into a pilot scale and produce also some of these monomers for the bioplastic production. So both in this part, both on the biosuccinic and this polyhydroxyalkanoate, they will produce these monomers that are known to be suitable for bioplastic production. And so part of the work will be starting from the bacteria and the biomass, extract these materials, so assess the yield, the purity, the productivity of the process. And this, so in the project, we have several companies, a couple of them that are expert in bioplastic production, so they will assess the quality of the material that we are going to produce. They are going to use these monomers to make actually real biomaterials. And then we have another two industrial partners that will assess how these bioplastics, if they are which kind of properties they have, and which kind of real life application we can think to use them for. So looking in particular into the market for packaging. So these are the more technical part of the work. Of course, in addition to assess the results, so how the material that we can produce from these waste streams, the quality of the material, it's really important to assess the sustainability. And so for that, our partner at the Imperial College in London we use a different kind of assessments, so a life cycle, a social life cycle assessment, and environmental life cycle assessment to make what is called an integrated sustainability assessment. So look into different aspects of sustainability, so of course economic, environmental, but also social and in terms of policy, to enable us to assess the technology that we are developing, what is the potential impact, and what will be the real benefits that we can drive into the society. In parallel to this sustainability assessment, of course, we also it is also important to design a market strategy. So there will be all our industrial partners, led by EcoResource in Greece, will use the results to make a market assessment and drive an exploitation strategy for the results that we are producing. All this work, of course, will be brought together, but all the communication strategies. So we start all the social media profile, the website is done online, and now we will start to put the first results and the activity of the project to disseminate them better. So I think that's all. As I said, we just started a few months ago, so all activities are just started. So I leave you with by thank you all of you for your attention. Again, I apologize for not being there today, and I also, of course, want to thank ACT for the support of our project.
Yes, thank you very much, Thomas. There is time for some questions. 2 questions.
Hello, Pierre Sersi from Sintef here. I had just one maybe naive question, but when you're talking about bioplastics, does that automatically make them biodegradable, or is not necessarily?
No, you are perfectly correct. Bioplastic, it does not mean it means that it can be bioplastic without being biodegradable, but in our case, they are biodegradable as well. So we are aiming for that. I should have pointed out, you're correct. It's a very important point, because if you have bioplastics that are not biodegradable, you solve part of the issue, but you generate some others. So
Hello, thanks for your presentation. I just have a generic question. For the bacteria, for the photosynthesis, the bacteria, is it any possibility for the bacteria like this to define something like the solar to chemical efficiency?
To define, you mean?
Solar to chemicals, for example, like the solar systems that for the solar photoelectrocatalytic system, something like this. For the bacteria, is it possible or no?
To quantify, yes. So we quantify that the efficiency is around 3 to 4%. So it's not ideal, but this is what it is. So their efficiency to convert solar energy into chemical energy is around 3 to 4% in the system we are using at the moment.
Okay, thank you.
Any more questions? Yes.
Yeah, Bahman Bohluli from NGI. I have a more generic question to all utilization or CCU projects. That's about extra renewable energy that we talk about. We rely on that to produce new products. I think we usually talk about renewable in terms of wind and solar. But these are, I don't know if we see the whole picture, if these are available in the quantity that we need. And electricity is the main, but when these are not needed, these wind turbines, they should do a great job when they are not needed, because we need for this material and also we need for hydrogen production. So I'm missing that holistic picture to see if we have that extra energy to produce other products. Thank you.
Thomas, would you like to react?
Yeah, I'm not sure I'm the most qualified to answer, but as far as I understand, so I'm not sure I got the question right, but so in our project, our Greek partners are aiming to use some extra renewable energy that in their case will be solar. In their case, their idea is that if they want to improve, to increase the power of the solar panels that they have installed, they will generate more energy, of course, during the day when they have the light peaks, but and then they have the issue of storing this energy. And so their approach, their suggestion is to use part of this energy to make hydrogen and store this energy as methane at the end of the process. So I'm not sure I'm able to answer in a more general way. This is the approach that our Greek partners are using.
Thank you. I think that this is also a very a question that indeed underlies all usage, but also, well, the flexibility that the future energy system will have is something that is really very interesting to think about. The mismatches between solar generation and nighttime use and the seasonal mismatches, etc. And that I would encourage you to consider during break, because we're going to break for 15 minutes now, back 4:15, and a last thank you to Thomas here, and off for the break.